Welcome to the Actuarial Academy. This is Dr. Me, and we're looking at a problem involving an actuary who models the size of insurance claims as the random variable y is equal to 10x to the 0.8 power, where x is an exponential random variable with mean 1. And we'd like to determine the probability density function of y. So this is a transformation problem, very standard type of problem that you very likely will find on the actuarial test. And I get the sense that these are the actual type of problems that they like. Ones that involve a little bit of a tedious effort and a little bit of algebra as well. So you need to know a couple of facts right up front, and that is you need to know the CDF of an exponential random variable. It's given as 1 minus e to the negative lambda x, where lambda is the expected value. And so when we actually work this problem, we'll substitute 1 in for this CDF. And also another fact you should know right away is that the derivative of e to the u is e to the u du. So this is a transformation problem, so I'm going to use what's most commonly used for these types of transformations, called the Cdf method of transformation. And you start out with the CDF of y, which is equal to the probability that y is less than or equal to y, and then you merely substitute in for y the transformed random variable because it's equal to that, and then you try to solve for x and isolate x. So let's review a little algebra here. We divide it by 10 both sides. The exponent on x is 0.8, so to isolate x and just solve for x, we have to find the inverse of 0.8. That's the same as the inverse of 4/5, so we just raise this side to the power of 5/4, just like that. And so this is good because now we have expressed the cumulative distribution function of y as the cumulative distribution function of x evaluated at this point here. So this is just equal to big F of x evaluated at y over 10 to the 5/4 power. And we can actually write out what that is because we have the CDF of the exponential random variable here, because x is distributed as an exponential random variable, so it's good to have the CDF already handy. So this is just equal to 1 minus, and so lambda is equal to 1, so we don't need to, we just leave that alone. And then we're left with 1 minus e to the negative y over 10 to the 5/4 power. And that is the CDF of y. Okay, so now we need to take it a step further, and we need to find the density function of y. And that's nothing but the derivative of our cumulative distribution function, big F of y. And let's work this out here. So this is going to be equal to the derivative of 1, 0. So we're left with negative e to the negative y over 10 to the 5/4 power times the derivative of this piece. So we're actually employing fact 2 now. So that's times 5/4, we'll bring that down, times the negative y over 10. I'll go ahead and carry the negative out here. This becomes y over 10. We subtract 1 from the exponent, so we're left with 1/4. But we can't forget one more step. We still have to apply the chain rule one more time here. So that's times 1/10. So that's the actual final answer. Now if you look at the selections they give you, you may not find it in this form or expressed in this form. So you may have to do some manipulations to get it to an answer that matches what they have. And sometimes they like to use decimal points. So let's go ahead and collect some terms here. That's 5/4, which is equal to 1.25 times 1/10. So this is just 0.125, and that takes care of those values there. And let's rewrite this piece here, 1/10 of y as 0.1 y to the 0.25 power. And the reason why I'm using decimals again is sometimes the actual test does represent things in decimals. So now we've taken care of all this, and then we still have one more piece, times e to the negative 0.1 times y to the 1.25 power. Okay, separate that, and that's our final answer. That is a PDF, the probability distribution function of our transformed random variable y, where y is equal to 10x to the 0.8 power, and x is distributed as an exponential random variable with mean 1. Thank you.